Okay, so today we're going to talk about Wright's table. So we have been learning about equilibrium, and that is when the forward reaction is happening at the same rate as the reverse reaction in an equation. So for example, if you have a reaction, A plus B gives you C plus D, the rate at which A and B is turning into C and D is going to be equal to the rate at which C and D is also going back and becoming A plus B. So when those rates are equal, we have what's called equilibrium. So we were able to solve for our K constant, our equilibrium constant, if we took the concentration of products to the power of their coefficient divided by the concentration of reactants, the power of their coefficient. But what is important is that those concentrations have to be concentrations at equilibrium. And therefore, if you are given information that is not at equilibrium, you cannot plug in and solve for K right away. And that is why we write these Wright's tables. It is a form of stoichiometry so we can figure out our equilibrium concentrations and solve for K. So R stands for the reaction, so whatever reaction it is, we write it out. It becomes like the header for our table. I is the initial concentration, so that's the concentration of the reactants and products when you are starting the reaction. Now, remember, concentration is molarity, moles over liters. So if we do not give you a concentration for something, then you assume that it's not there at the beginning of the reaction. Its concentration is 0. The C is the change in concentration, so you'll either subtract from the reactants or add to the product, and we will use X as our variable for change. Equilibrium concentration is what is the concentration once we are at equilibrium. Again, we can plug into K, and it is a concentration, so it's molarity. So the first step is to write your Wright's table. The second step is to write your K expression, and the third step is to plug in and solve. So we are going to do an example together. What I want to point out is that this is stoichiometry, so your change in X has to do also with the coefficients. So if you have a reaction where the coefficient is not 1, let's say it's 2, your change in X, if this was a reactant, would not be just minus X, it would be minus 2X. So we'll take a look at that. Alright, so here's our example. At a particular temperature, 12 moles of SO3 and 3 moles of SO2 is placed in a 3-liter rigid container. This word placed is key. At the beginning of a reaction, you're going to put these products or reactants in, depending what they are. So that means these are initial values. SO3 dissociates through this reaction. We're given the reaction here. It's nice and balanced. And then at equilibrium, you have 9 moles of SO2 present. So that means that this is an equilibrium value. So that's important when you write your Wright's table to know which things are initial, what's there at the very beginning, and what's there when you reach equilibrium. Because remember our graph, if we have over time and we have our concentration, maybe your reactants are up here, your products, you have a little bit of them, but over time it's going to change. And when that change stops, that is when we hit equilibrium. So initial concentrations and equilibrium concentrations are not always the same. Okay, so we're going to write our Wright's table. R, I, C, E. R is our reaction, which we have, 2SO3. Remember now our arrow goes in both directions. It's an equilibrium reaction. All right, we're going to write our initial values. Now remember, initial and equilibrium is in concentration. I give you moles, but you all know how to get concentration from moles. Concentration is moles over liters, so we must do 12 divided by 3, which is 4. We have another one, 3 divided by 3, which is 1. And our equilibrium is 9 divided by 3, which would be 3. So we have 1, 2, 3 concentrations that we know that we can plug into our table, and we must put them in the right spot. So the 4 molar goes for SO3, and it's initial, so I'm going to put that here. The 1 molar goes for SO2. It is also initial, so I'll place that there. If there is not an initial concentration for a product, that means you're going to write 0. It's not there yet. It will be at equilibrium. All right, so now we're going to have our change. Remember I said we subtract from reactants, add to products. We're going to use X, but how many X's you have depends on your coefficient. So minus 2X plus 2X plus 1X, or just X. Now, our equilibrium concentration, we actually have a number for one of them. So we're going to plug in this number for SO2. All right, so now we can solve for X because I have an initial and an equilibrium concentration. If I know my change, I can solve for X. So 1 plus 2X equals 3. Well, this is an algebra problem. Subtract 1 on both sides. 2X equals 2, so your X ends up being 1. We know our change. Our X is 1, so we can replace 1 for X in our Rice table. So 4 minus 2 times 1, 2. 0 plus 1, 1. We now have all 3 equilibrium concentrations so that we can solve for K. So remember to write your K expression. That's the next step. It is product over reactants. So SO2 is a product, and we take it to the power of the coefficient, which is 2, times the concentration of O2, power of a coefficient. That one is 1. And then on the bottom, we have our reactants, SO3 to the power of 2. Good. Well, you can only plug in E values, which we have. E values. So we can do that and solve. So K is equal to 3 squared. Be careful on your calculator. Put the exponents inside the parentheses. Times 1 divided by 2 squared. So if we rewrite this, that's 9 over 4. Plug that into your calculator, and you should get K is equal to 2.25. All right, so that's how you find K with a Rice table.